Hello, I'm Mr. McChesney, and today we're talking about momentum. So we have a problem here where two cars are colliding. So if we look at the problem, it says the speed of a 1,325 kilogram car, which we'll call C, is moving north at 27.0 meters per second. It collides with a 2,165 kilogram car, which we're going to call D, moving east at 11.0 meters per second. The two cars are stuck together. In what direction and with what speed do they move after the collision? So if we look, we've got car D, and it's moving to the east. Car C is moving to the north. When they hit, they go off at some angle that we're not sure of. So if we use vectors, we have, for instance here, 11.0 meters per second. And I definitely want to label my other vector as 27.0 meters per second. And we show the direction, and that vector is for car C, so that's VC, and I put a little I to mean initial speed of it, and it's going north. So that's what we have over here. Car C, which is moving faster than car D, so its vector is bigger. At the head of that one, right there, is where you put vector D for car D's velocity, and then its momentum going to the east. And when you add these, you draw in your last vector from the tail of one to the head of the other one, and that's your resultant vector. So that's for the resultant velocity, and will also then be resultant momentum when we figure that out. So as we work through this problem, we want to write out all the information we know. So we know that the mass of car C is equal to 1,325 kilograms. We also know it has a speed, and we want to call that VCI for velocity or speed of car C initially, which is 27.0 meters per second. And always put your units with your numbers. Then we have car D, which has a mass m little d of 2,165 kilograms. It has a velocity to start, so we'll call that V sub d I for initial velocity, and that is, oops, made a mistake there. Let's erase that. It's not 27. And that's one thing you always want to check and make sure you're writing these numbers down correctly. So we got 11.0 meters per second. So now what are we looking for? Well, in order to find momentum, we need to know what our mass times velocity to start is for both things, and it's going to be equal to the mass times velocity that we finish with. So that means we need to figure out what the velocity of car D plus C, since they're together, what that's going to be equal to. And then it also said in what direction. So that means we need to know what our angle is going to be. And many times you use the Greek letter theta, which is a circle with a line through the middle of it, to represent an angle that you don't know. So now let me show you how to figure out the momentum for one car. So momentum is the Greek letter rho, which looks a lot like a little small p. So the momentum for car C to start would be equal to its mass. If you look back in the chapter, you'll find this equation: the mass times the velocity of the car to start. And in this case, its velocity is all in the y direction. So I add that symbol also to represent the fact that it is moving up. So I can plug my numbers in. What's the mass of my car? I look back at my starting information. It's 1,325 kilograms. Then I'm going to multiply that times its velocity, 27.0 0 meters per second. So the momentum of my car to start is equal to 3.58 times 10 to the 4th power. And now what are my units? Well, I had kilograms to start, and they were multiplied by meters per second. None of those things cancel each other out. So my units are kilogram meters per second. So the momentum of my blue car to start, P little d I, is going to be equal to the mass, just like before, the mass of d times the initial velocity of d. In this case, d was moving east, which is in the x direction. And if you plug your numbers in that we wrote initially, you should get an answer of 2.38 times 10 to the 4th power. And again, you need your units. Kilogram times meter per second. So now we know our initial momentums. You use the law of conservation of momentum, which says that your starting momentum has to equal your final momentum. So my final momentum, and if we look at our diagram, our vector diagram here, we have a right triangle. So we got our starting momentum in the northern direction, our starting momentum in the eastern direction, and we're going to get some momentum at an angle. So that looks like a right triangle. The Pythagorean theorem would be very helpful here. So my final momentum is going to be equal to the square root of my starting momentum for both cars, so PCI in the y direction plus PDI in the x direction. And with Pythagorean theorem, you're squaring both of those terms. So if I put in my numbers, I'm going to get, my numbers are 3.58 times 10 to the 4th kilograms times meters per second, and that's going to be squared, plus momentum of my car D, 2.38 times 10 to the 4th, same units, kilogram meters per second. Again, you got to square that, and all that gets square rooted. So my momentum final, the magnitude, which means amount or size of, the momentum final of that is going to be 4.30 times 10 to the 4th power. And since all my units were squared and then I square rooted them, the units, when you add them together, since they're the same units, don't change. And I get kilogram times a meter per second, which is a unit of momentum. And one last thing about this, check and see if your answer makes sense. So I had a right triangle. The sides of my triangle were 3.58 times 10 to the fourth and 2.34 times 10 to the fourth. My hypotenuse has to be the largest number, the largest size, 4.30 times 10 to the fourth. So that makes sense that it's the largest of those numbers, which should mean it's a realistic answer. Okay, so as we saw, we found our final momentum. But really, since it's a vector quantity, we need to have an angle associated with this. So I'm going to solve for this angle on the diagram we've drawn here, the one we call theta. So when solving for the angle, we've got opposite and adjacent side, so we're going to use the tangent function. And when you try to find an angle, you have to use the inverse or arc tangent, which on your graphing calculator would be second tangent normally. I'm going to use my opposite side, my momentum in the x direction, or that was my d car, and I'm going to divide it by the momentum in the y direction, my adjacent side, which was my c car. So now I plug my numbers in. So I'm going to do second tangent, or inverse tangent, of my numbers. So my momentum of my d car in the x direction was 2.38 times 10 to the fourth power, and you still need your units, kilograms times meters per second. And I'm going to divide that by my momentum in the y direction, 3.58 times 10 to the fourth power, same units, kilograms times meter per second, close my parentheses, and my units, I have kilogram times meter per second on top, divided by kilograms times meter per second, so those units will cancel out. And I'm going to get an angle of 33.6 degrees, and since we measure our angle down from the northern axis to where we finished, so that means we went east of the northern axis. Now, you can also report this angle as the angle from the horizontal or the angle from the eastern axis, and if you do that, that angle would be 90 minus the angle we just found. So 90 minus 33.6 degrees, and that's going to give you an answer of 56.4 degrees. And that angle, you measure it going from the eastern axis up towards the northern axis, so we call that north of east. And either angle is correct. So now your answer is going to be, I had a final momentum of 4.30 times 10 to the fourth kilogram meters per second at an angle of 33.6 degrees east of north. And the very final thing we want to do is it asks for, in the problem, it said, what speed did they move after the collision? So we have to find our final speed. So to figure out our final velocity, we have to use the law of conservation of momentum, which says that the initial momentum equals the final momentum. So if we're going to do that, our final momentum, which we know the number for, would be equal to our mass of our car, and a car now is the mass of C plus D So you have that mass times the final velocity of those cars. So we want to get it so we have final velocity by itself. So in order to do that, we have to divide by the mass of car C plus the mass of car D on both sides of the equation. So my final momentum divided by mass of car C plus car D. If I do that, I cancel out the masses on the front side of on the back side of the equation there, and I move them over. So I'm solving for final velocity. So I'm going to plug in my answer for my final momentum, 4.30 times 10 to the fourth and my units on that are kilogram times a meter per second. My mass of my first car was 1,325 kilograms. And I'm going to add that to the mass of my other car, which was 2,165 kilograms. And since when I add those two numbers together, I'm going to get a kilogram on the bottom, a big number for kilograms, and the kilograms will take away the kilograms on the top of the fraction. So my units are going to be meters per second only. And we are having an answer for speed, which should be in meters per second. So that should give us a correct answer. So we get 12.3 meters per second. Now if you did this problem in your graphing calculator, you may find again that if you don't put a parentheses underneath this and you did it all in one step, you're not going to get the right answer. So check your work and make sure you end up with 12.3 meters per second.